Okay, so hello again, and today we will try to do some course project calculations related to the codes we have discussed approximately 1 week ago, including Huffman and Shannon-Fano codes. Now, in the tasks, if we check them, you will see that there is actually a little bit more to it than just design a code. We need to do some calculations. Well, we'll cover today task number 2, task number 3, number 4, and 8, I believe. Yes? Yes, that is also. So quite a lot of points to be closed. What we'll have left is task number 5, task number 6, but they will be quite big tasks. Don't worry about that. So in task 2, what we need to do is some initial calculations. What is your data source about before actually making Huffman Ocean on our code. So here we estimate something called the information volume per symbol. So how much each of these table symbols like here is actually transmitting. Yeah, so how much information does A1 have, A2 have, and how much do they have on average? Yes, because that's actually information theory, and there were video records which I asked you to study covering this topic. That basically, the more unexpected symbol it is, the higher is its information. But that works in other way around too. So if your symbol is unexpected, then others might be more expected, which reduces the overall information. So what we want to know is not just how many information is A1, how many information is A2, A3, but what is the average amount of information per all of them. That is called an entropy. Yes, the entropy can be calculated by a formula which is available here in materials for the source like follows. Yes, so you take the probability of the symbol, multiply it with the logarithm base 2 of that probability, and do so for every symbol that you have. So you have 7, 8, 9, 10 symbols. You calculate this product for each of them and add everything together. So basically, you need to remember that logarithm of number that is less than 1 always negative, and we don't want our information amount to be negative. Because of that, we compensate with this sign of minus. Well, essentially, we can rewrite the same formula slightly differently. Yes, like this is actual, oh, sorry. This is actual information of the symbol JAI. Yes. So that's how much information this specific one symbol contains with the probability P of the I. Yes. Now, what we do here in this part is actually calculating the average. However, here you need to realize that the probabilities of these events are not the same. So it's not like average arithmetical, it's more like a mean of the distribution. Yes, like the full probability formula. Like, say, you have um, this. Oh, well, actually, it works the same if we kind of look at it of some specific dice. Yes, so let's say you have some dice rolling, which can be 1, can be, I don't know, 2, can be 3. And when you roll it, there is the probability to roll each one of them as 1 versus 6. So you can calculate what is the average value you are going to throw on these dice by calculating probability of getting 1 multiplied by 1 plus probability of getting 2 multiplied by 2 and so forth. That's how actually average value should be calculated, yes, and that's how it is calculated. 1 versus 6 multiplied by 4 plus 1 versus 6 multiplied by 5 plus 1 versus 6 multiplied by 6. So probability with some number. However, since this is a, we can say, fair dice, yes, which has the same probabilities, we can actually put that number outside of brackets like so. 1 versus 6 multiplied by 1 plus 2 plus 3 plus 4 plus 5 plus 6. Yes, and then you get the formula of the arithmetical average. Yes, for this specific case when all probabilities are the same. But normally, if the probabilities are not the same, you actually go through the full formula. Yes, like here. So that is also called an entropy. Now, as you know from thermodynamics, yes, entropy actually describes the chaos. Yes, so the higher is entropy, the higher is chaos. And the same happens for information. So as we discussed, the more chaos in text, the more informative it is from the point of view of information theory. Yes, as people, maybe we don't understand there anything because we need redundancy, we need extra repetitions and all that stuff. But purely efficiently wise, yes, for telecommunication system, if we send as concentrated as possible, then that is good. Now that is depending clearly on your probabilities distributions, yes. So let's now actually try to calculate this entropy for the source that we have. So first things first, I am going to actually define the source that I have. So I'm going to write that in CLC, clear variables. Let's say that now we are working on task to calculate entropy and other parameters like redundancy and stuff like so. So first of all, I'm going to need to have these source probabilities. I am going to demark them with P as a vector 0.12, 0.14, 0.07, 0.11, 0.12, 0.06, 0.08, 0.15. You can actually write them in the correct order, if you, well, sorted order if you want to, but also MATLAB can sort that for us quite easily. Will be sort of P. Yes, so if I run it like this, yes, I also need to save it somehow. Let's call this course project 2025 task 2, 3, 4, and 8. So now it's sorted in ascending order. We wanted actually to have descending. So let's get a help on sort to see how we specify this parameter. Yes, so there is a parameter you can specify. Like mode, I believe. Yes. Wait. So ascent or descent. Yes. So you see that there are valid modes. Well, dimension is irrelevant here, so I'm not going to specify that. Empty brackets. But for this one, I actually want to have descent. No, just descent probably. I don't need to count. Yes, so just like that. So you see now it has actually sorted it for us. Another good things to do is to, well, let's have printf display sorted probabilities. Another good thing to do would be actually check if they all add up together to 1.0 if there is some mistake, because it can happen. Sometimes it happens, yes. So also fprintf check if all probabilities add up to 1.0. So that will be summation of p. Well, yes, in my case it's precisely 1, so everything is fine, we can go further. If it's not, double check first of all if you entered it correctly, and if it's still not, then we can change a little bit your source so that it becomes so. Yes, maybe somewhere it's a little bit extra, maybe somewhere it's a little bit less. Okay, so that's first point. Now that we have these probabilities, we can use this formula of entropy to calculate the average amount of information per one of the symbol in bits. Yes, so we have like how many of the symbols we have here? 9 symbols. Each of them can be encoded in binary form. Yes. Well, and how many bits do we need is actually what this entropy answers. Like you need this many bits to encode one of these on average. On average, true. Yes. So what is this number of actual information in bits per symbol? Let's just implement this formula. So there are multiple ways to do so. Actually, you can create a for loop and go through all these probabilities. You can multiply them element wise, each with each other, and add them together. So I'm going to be in to do the most advanced stuff. Yes, let's say fprintf entropy of the source. Well, actually, I'm going to first calculate it. So calculate entropy h is going to be probability element-wise multiplied by logarithm 2 of this probability, also element-wise. So we can say like probability with a dot by log 2 of probability. So that is going to multiply element-wise, first with first, second with second, third with third, and so forth. Then you need to add them together and change the sign to minus, because logarithm of number less than 1 is negative, yes, and information amount can hardly be a negative number. I'm going to put the semicolon here, and instead I'm going to show this as a 0.2 floating number with 2 symbols after the comma, and that is going to be this h, and also new line. So that's going to produce some output for us. Let's check if I didn't make any mistakes. So entropy of the source is 3.11. Actually, let's also add units like bits per symbol. Okay, so that's 3.11 bits per symbol, meaning that on average, I'm going to need to have 3.11 rectangular pulses for each of the symbols. But that's impossible, yes? I need to use either 3 or 4. There is not really much choice for me, which means that actually this last symbol here, bit, well, not bit is an amount of information, but let's call this a binary symbol, yes? A pulse, rectangular, 1 or 0, is actually underworking, underperforming. Yes, it could have transmitted more information, but there is just none. Yes, so this is amount of information on average per one of the symbols. Now, if you recall the video record of lecture, then this entropy, well, the higher is this entropy, the better. What is the case of having the maximum possible entropy for this source? That is going to happen only on one condition: if all the probabilities P1, P2, P3 are exactly the same, which again makes completely full sense from the standpoint of view that we analyze chaos. Yes, so if any event is equally possible, then that is maximum chaos. Yes, you absolutely have no idea what's going to happen next. Each of these is completely possible and equal to 1 versus n. In that perspective, actually, now our formula of entropy, log2 of P with a minus sign, is converted into 1 versus n by log2 of 1 versus n. And also the minus sign doesn't go anywhere. Now, it doesn't depend on any I, starting from 1 going to n. So essentially that means well, that basically what we are going to do here is 1 versus n plus well, log 2 of 1 versus n plus 1 versus n, blah, 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 plus the same stuff. So basically we do that n times. So essentially it can be written like n multiplied by this stuff, canceling out this one, and we are left with the minus log 2 of 1 versus n, which according to school formula can be rewritten as log 2 of n. So that is the maximum probability which is observed in the case when every symbol is equally possible, yes, which is maximum chaotic situation, and its number is supposed to be bigger than this one. Now, the idea of our Fanon-Fanon or Huffman code is to approach to this number. So you will know that your code actually works or does not if your average code word length m is going to be more than original entropy, but less or equal than maximum possible entropy. If that is the case, then there is actually effect of your code that you have designed, which means that probably it works correctly. So because of that, we calculate these values, yes, to actually verify that. So now let's calculate maximum entropy. And one more thing here is that actually I can even go like this. I remove this summation, I remove these brackets, I remove this point, now forcing it to work as a matrix product, vector row by vector row, which I transpose here. So now I have vector row by vector column, so it's going to multiply each with the other and add summation in one command. Yes, so basically this is the same stuff, and the number is going to be also the same. Yes, so nothing changes. So let's calculate hash max, which is log 2 of n, which we don't happen to know. So let's actually find it out. N is length of p probabilities. I'm going to copy this fprintf. Maximum entropy of the source. So if I run it now, you see that indeed this number is slightly higher. Not much, but slightly still, yes? So that means that there is actually room for improvement, and using the Huffman or Fanon code can give you effect. How big, that is also unclear from this specific situation. But we'll see. Okay, so what else do we need to calculate in task 2 was the source redundancy. So what is this excess information, this extra that we try to get rid of by running compression? So basically this redundancy is what the compression is actually removing. And it's calculated as the ratio, like current entropy versus maximum possible, like how much of efficiency are we, and 1 minus efficiency is this redundancy. So basically, let's calculate that redundancy. Calculate redundancy in percentage. So that means I'll call this redundancy as 1 minus h versus h maximum multiplied by 100, because I want to convert that into percentage. Now this is in bits per symbol and this is in bits per symbol. So now we have dimensionless unit, normalized one, yes. So we add fprintf statement, redundancy, the source. Well, one sign after comma will be fine, I believe. And but I'm not sure how I put the percentage sign. Maybe like so. Let's find out. Redundancy. No. Just a minute. So don't remember. So MATLAB printf percentage. Percent sign. Double percent. Okay, I see. Because this person here, as you can see, is placeholder for some format which we are going to use. And so here we say that this is actually person symbol. So redundancy of the source is 2.0%. So that is how much our source has unuseful extra information that we want to get rid of. So we can see that in my particular case, it's not much. So we already can say that it is almost optimal source, which still probably can be improved a little bit by running a compression. So we'll have, as we discussed last time, two codes. They are slightly different, both of them, Chenon-Panot and Huffman, which happen to produce different code words, and we'll numerically compare them to conclude about their efficiency. So that brings us to the task 3, yes, for which we now need to have this table of your code word, how many symbols are in your code word, how many of them are ones, and how many of them are zeros. So actually, let's input that data now to the code. I need to see it here. Now, pay attention that at this point you have to be sorted, like here, yes. That's why I did use sorting here, because they need to match. Yes, the probability 0.15 needs to match these two because they are about the same symbol. Now, if you didn't do this sorting, then you really should, or at least have them written manually in the sorted order. So that's going to be task 3, parameters evaluation after Chenon-Panot Huffman coding. So basically we'll have mi, m1i, m0i. 3 arrays we need to fill in with how many symbols are there, how many ones and how many zeros. Now I'm going to do first 2 of them, which are 2, 3, 3, 3, 3, 4, 4, 4, 4. Yes, so 9 of them together. Of them, ones are here 0, 1, 2, 1, 2, 2, 3, 3, and 4. And obviously number of zeros is number of total symbols minus number of ones. But if you prefer, you can also input them manually. So number of code symbols. Pay attention, they are different lengths, yes, so more common symbols are shorter and less common symbols are longer, as it should be. Number of ones per code word, and this is accordingly number of zeros per code word. Okay, now as you can see, this number is integer number, yes? So there is no such thing like 0.3 symbols, 0.1 symbols, and stuff like that. But they are different. So on average, this average length is going to be fractional, yes, non-integer, which is fine as long as each specific symbol is still integer length. So let's calculate average code word length, aka entropy after coding, because that's basically it. Yes, that's how many bits are per symbol, which is log2 of probability. So in our formula, therefore, we basically have to put it, sorry, here, instead of log2 of probability. Yes, so in normal entropy here, we were having log2 of the probability. Now, after we did coding, there is specific length of that symbol, no longer related to this probability, and also minus sign is gone. So this is basically the same formula. Same way, we estimate also average number of ones per symbol and average number of zeros. So let's estimate all of them. So M average is going to be M, probability P, vector-wise multiplying by M transpose. Yes, so this way it adds summation. Like if we have 1, 2, 3 multiplied by 4, 5, 6 matrix-wise, and that's going to produce me 1 multiplied by 4 plus 2 multiplied by 5 plus 3 multiplied by 6, which is 32. One number, yes? So the same way it works here. I just make sure that my M, actually not M, but Mi, is a vector row, which I convert into column, and probability P is also vector row. So vector row needs to be multiplied by vector column. So that's average code word, length, number of symbols, M1 average, probability by M1I transposed, average number of ones, well, and the same way also average number of zeros. Now, this average number of ones and average number of zeros are of not so big interest for us in themselves, but we can use them to calculate what is the probability of getting 1 and what is the probability of getting 0 in your message. And as you know, in a chaotic and optimized system, this should be as close to 50-50% as possible. So that's what we need to verify. So fprintf entropy after encoding that is going to be m average. But first let's check out how our entropy changed. Well, actually, in my case, it even reduced a little bit, yes? Again, for this particular code, it happens so. If I check another code, it might be slightly different, so we'll see with the Huffman code. But it still can, yes, we were expecting it to become closer to this one, but from the looks of it, it seems it's not going to really happen, so that means that this code is not so efficient. And we are speaking about trying to optimize this just 2%, which in itself is already a very small number, yes? Now that happens because this data of the sources is actually synthesized. I didn't take any texts to calculate number of letters, yes, and calculate their probabilities, but instead randomly generated some numbers for you. Now, in realistic texts, yes, actually there will be much more uneven distribution and even much more symbols as of such. But we'll see how the probability of 1 and probability of 0 are actually here. Yes, so let's also fprintf probability of 1, which is none other than M1 average versus M average, and probability of 0. M0 average versus M average. So from this perspective, we can see the probability of 1 is 54% and probability of 0 is 46%. So they are quite close to 50-50, not ideally close, but again, it's tricky to get them exactly equal. Yes, that's a lot depending on your source, and your source is specified by some computer program in your case, so it is what it is, yes, and you basically get this result. All that you can do maybe try to do your code a little bit differently, but is it really worth it? We'll see when I change to Huffman code. Actually, let's do it right away because I have them ready and I have slightly different statistics here. So let's do that. Shannon-Fano. So that is going to be Shannon-Fano. And the same ones I'm going to make for Huffman now by simply copying this entire stuff and commenting these lines. So that's going to be Huffman. And I also need to change these numbers accordingly to this table. I'm going to be all of them 3s except last two. And here it will be 0, 1, 1, 1, 2, 2, 3, 2, 3. So we had here entropy of 3 and average is 3 precisely. So on average, the length of the code word is accurately 3.0. Yes. And the probability of 1 is 0.54. Probability of 0 is 0.46, which is more or less balanced. Yes, actually. Now let's see how well it will work for the other code. Now you need to realize that I could have also, and I did show, I believe, that make the Shannon-Fano code differently. Now Huffman code is more specific, more strict, we can say so, yes, and not much freedom there. Here, however, I could easily split these two groups slightly differently, and that would change the code entirely. So let's see about Huffman code. So as you can see, Huffman code is exactly same, except that probability of 1 or 0 is inverse, but you can again easily replace every 1 with 0, every 0 with 1, and that's going to be the same code. So essentially we can say this is the same, exactly same, Huffman or Shannon-Fano. Is it really worth it to go a big deal and try to, make different code variants? Well, based from these computations, we can see not necessarily, as well as not necessarily we are going to get entropy improvement, yes? Now we can calculate entropy for these binary symbols, yes, and see how close it is to 1.0. H binary, yes, probability of 0 multiplied by log 2 of probability of 0 minus probability of 1 multiplied by probability of 1 log 2, yes. So let's do that too, because in a sense, that's what is the most important. Our sequence is more or less reduced to the binary sequence of ones and zeros, and we are interested to know what is the entropy of binary data of ones and zeros. H binary, which is going to be minus well, it would actually make sense to save them. P1 and P0. So probability 1, probability of 0. So here I have P1, here I have P0. Now that I have them saved as variables, I write P1 multiplied by log 2 of P1 minus P0 multiplied by log 2 P0 and fprintf binary entropy. Printf bits per symbol, maximum is 1.0. As you know, for binary data, if the probability is 50-50, then log 2 of 1 versus 2 is minus 1, yes, and accordingly, minus 1 minus 1 is versus 2, yes, because we also have 1/2 as probability, is going to produce this probability. So that's for case when 1 and 0 are exactly same probabilities. I need also to put these quotes on, like so. So binary entropy is actually very close to 1.0. Yes, so we can say that from the perspective of binary data, we are almost optimal. Well, let me just add new line here. So what else did we need to calculate here is data transmission rate after your compression and the compression ratio. Yes, what is the compression ratio? Which is not high, but again, this is code without um, changing your data. This is um, non-destructive compression that maintains data originals. Yes, destructive compression can achieve higher compression rates, but um, that comes at a cost. In our case, we speak about symbols, well, about alphabets, so we don't want to have any distractions there. So let's calculate these remaining parts, like data rate and the compression ratio. I'm actually going vice versa, so first compression ratio, which is the letter for that K, so that is M average versus the entropy, F printf. Again, this is dimensionless unit, yes, because it has same dimensions for M average and entropy. But in our particular situation, as we can see, we actually didn't achieve quite good compression rate. Or wait a minute. So 3 versus 3.11, something is not correct here. Wait, so M average is actually... wait a minute. See, I have specified incorrectly here. So it's just like this 3 point something is not showing what is after comma. So it's rounded and moved a little bit. So I have a formatting problem here. It needs to be like this. That's why I was confused, because my compression ratio actually shows that there is a positive effect of code, but my entropy shows that there is not. So that means somewhere I have a mistake. Now, entropy after encoding is higher than entropy before encoding, but still not so high as the maximum possible one, which makes sense. Yes? And the compression ratio, well, is 1% that we were able to actually benefit from this compression. But still, 1% of billions of symbols is noticeable, yes, and can be used to optimize the multi-user systems, modern internet, and stuff like that. So we can't say that it's nothing, yes. Mm, yes, also I wanted to add the units here, bits per symbol. Okay, next is the data transmission rate. This is actually called bit rate. Yes, like if you do some streaming, listen to some music and online video, online audio, you see there is this bit rate, which actually quite often is variable, changing, yes, because of compression. Now those compression algorithms are destructive. Lose they do lose some of information. In our case, it's fixed bit rate, yes. So let's calculate what is this bit rate. Now the bit rate is calculated as amount of information that there is in the symbol actually versus the number of symbols you used for coding of that symbol multiplied by duration of each of the symbols. So now you also need to specify the tau parameter, which in my case is symbol duration is 60 nanoseconds. So let me go to the beginning and specify it here. I will also mark it so that you see that T symbol is 60 E minus 9. So symbol duration. Now we can calculate this bit rate, which we normally denote with R, so that is entropy versus M average versus T symbol. F data generation rate. So that shows how fast your source is producing information. That's bits per second. Well, or how they put it, BPS, yes, bits per second. And accordingly, that is R. So let's see. So we generate like 16 megabits per second, something around those numbers, which is actually more than different streaming platforms and so on, but only because we have here not really high compression rate. Yes, we don't use high compression rate codec like commercial products really do, because we don't really want it to. Now the question is, will your channel with noise be up to the challenge to transmit that speed? Yes, because on one hand you have the source generating this amount of information, then you have a channel which has a limited capacity. And there is also noise, which theoretically reduces the capacity of your efficient capacity of your channel. And if noise is too strong, yes, then you can come up with a situation when your R is going to exceed the capacity of your channel. Well, that's like trying to look 4K video on YouTube using some dial-up modem, very slow, laggy, and so on. Yes, not going to happen. Same simulation, same situation here. So let's find out. For that, we are going to go to the task number 4 to do some channel-related calculations and checking if the Shannon's theorem's condition is true, meaning that if you design some error correction code, will it be possible to protect message from errors, or that's impossible because of the condition not being true. So what we want to know here is what is the channel capacity, data transmission rate without noise, what is the bit error rate, so what is the error probability for your specified modulation and signal to noise ratio, and what is the capacity with this noise. So formula wise, the capacity, that is maximum transmission rate without noise, is very simple to calculate. That's basically number of pulses per second. How many pulses of duration tau can you transmit in 1 second? Now, error probability can be calculated by one of these formulas and is necessary to estimate the capacity of channel with noise. Obviously, the more often errors are happening, the more often retransmit is necessary, which reduces your efficient data transmission rate because you transmit the same stuff multiple times, yes? So that's how it's working. Of course, we can say that we can design some error correction code, but as you have learned today, in order for these error correction codes, you have to add control symbols, which again reduces the speed of your actual information transmission and still utilizes your capacity. Yes, so either way, we have to have some reserve, some extra left comparing to that. But that's completely depending on your signal to noise ratio and modulation type. So let's calculate these three formulas. So that's going to be task 4, capacity with noise, without noise, and with noise for channels. Well, let's start with the capacity without noise, which is 1 versus t symbol. Capacity without noise. Fprintf, channel capacity, no noise. Also bits per symbol. C binary. Now, right now, everything should be fine, and the capacity without noise is actually more than data generation rate, which is the condition of the Shannon theorem, so that R should not exceed the capacity, plus some arbitrary small epsilon, yes, as mathematicians like to say, some reserve, and so forth. So as long as we don't have noise, everything is fine. But noise is going to reduce this capacity. And what's going to happen then? Let's see that. Before that, however, as you have seen in formula, we need to estimate the probability of error depending on your signal to noise ratio and modulation type. So my signal to noise ratio was 12 decibel, and I use all 3 types of modulation. Let me actually add this information. So SNR is 12.0, SNR in decibel. And modulation wise, I'm going to calculate all 3 error probabilities, like P error BASK, P error BFSK, and P error BPSK. But you only need to do one, yes? Now, this involves using something called an Euler's function, yes? Which can in MATLAB be implemented by this error function. So I believe we should create an anonymous function. So define Euler's function as anonymous function. Just let me double check fast how that was working. MATLAB anonymous function from the help. So you specify the name of the function you want to put equal, then put the at, the argument you want to use inside that function, and then the function expression itself. Yes, so in our case, considering we'll call the function phi, and that will be a variable of some, let's see how it was called here, x. Well, okay, let it be of x. Oh, sorry. And then the text of this function. Yes, so 1 versus 2 multiplied by 1 plus error function, erf, which is like that, x divided by square root of 2. Now we do have this phi function for which we now need to calculate the square root of the signal to noise ratio. However, pay attention that the signal to noise ratio here is in times, in linear scale, not in decibel, so we need to do this conversion. Let's call this like so. The conversion is done as 10 at the power of SNR divided by 10. So this is also SNR, but this is linear scale in times. Yes, it's dimensionless unit because you divide power with power and get no units. Okay, so that means now we can specify these three error probabilities. Like this phi function is actually calculating your probability of not having a mistake. So what we want to know is actually the opposite event. Yes, what is the probability of having an error? So phi of square root of, for amplitude shift keying, you have 0.5 of this signal to noise ratio. Now for frequency shift keying, you have 1. Well, I'm just not going to write it. And for phase frequency shift keying, you have double. Oh, sorry. Like so. So it calculated fine. Now I can output the results. F print F. So BASK bar is equal to not sure which format I should use. Maybe exponential. Let's check it. And basically, I think I would like to calculate capacity. CBSK, CBFSK, CBPSK, while we are at it to display them both. So capacity is calculated as the similar formula. If you recall, here we have logarithm by probability, probability by logarithm. So you can consider this as the entropy of noise. On the second hand, 1 is maximum Ash binary. So maximum binary entropy minus entropy of the noise. So the total entropy of the channel is going to be reduced by the noise, which makes sense. Noise actually, disrupts your signal. So from that perspective, and minus was gone because here we have minus, minus. Yes, this minus compensates this probability. So basically in entropy formula, there was the minus and you have subtraction here. So either way, let's calculate that as 1 plus VR BASK by log 2 VR BASK plus 1 minus PR BASK by log 2 of 1 minus PR BASK. And all of that needs to be divided by symbol time duration. So if there is no noise, again, this makes perfect sense, yes? If there is no noise, then this entropy is 0, and you are back to this formula. So, the same formula will be for frequency shift keying and phase shift keying. Again, you only need one. I'm doing all of them just for demonstration purposes. So I need to change it in 4 places. And here also 4 places. And now I'm going to make a print statement to display it all. Error probability and the capacity. Now going to F, beats per second, new line, that will be PR BASK, C BASK. and the same stuff for all the others, so that we can actually compare FSK, 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 and FSK. Sorry, PSK here. Now, what we can see here is that as we change modulation from amplitude shift keying to frequency shift keying and phase shift keying, so frequency and phase shift keying, the error probability actually decreases. Just like we mentioned that in the lectures, that the amplitude shift keying is the worst of them, and phase shift keying is actually the top resistant modulation type that there is actually. You can see that the probability of error is 1 per billion, yes, and the capacity wise, it's not really changing really much, yes, just some number here only, literally in bits per second. Now, for frequency shift keying, it's also good, but not too good. And for amplitude shift keying, you can see that now this capacity is, maybe it's difficult to see for you, so it's 1, 6, 2, 5, and so on. Whereas this data generation rate was 1, 6, 5, 4, and so forth. So now we can see that for the binary amplitude shift keying, the Shannon theorem condition doesn't hold, meaning that no matter what kind of coding you invent, it just cannot be helped. Yes, this is already fundamentally impossible to be transmitted without errors in such conditions. Now, if we switch to frequency shift keying, that changes error probability like 100 times, but it's sufficient to fix this problem. Yes. So, depending on your modulation type, depending on your signal to noise ratio, it is possible that this condition will not be satisfied. Don't worry, that doesn't mean that you don't get a good rate and stuff like that. It's just the task as it is. It's the purpose to actually verify, is it possible or not? And regardless of this result, we are then going to do the coding, not even considering this situation, because obviously what that says is that having coding for this channel probably is not going to work well. We need some stronger codes that can fix 2 or 3 errors in one code word. Now for this one, frequency shift keying, actually it might work well. But again, we'll speak of this more on the final classes of our course, when we will actually have something to prove that we're not just our opinion or consideration, but in fact some simulation results that will clearly show is it so or not. Particularly also for the point of 12 decibel. So finally, the final task is task 8. Task 8. Estimate possibility of 2 plus errors in code word. So we'll be designing Hamming code. And as you have seen today in lecture, if you have more than one error in Hamming code, then it starts to work incorrectly. So we want to know what is the chance of that happening given your error probability. So how often this will happen? Maybe you shouldn't use Hamming code in that case. So this is going to actually answer you, is it acceptable or not to use the Hamming code in these conditions? And again, as before, I am going to calculate 3 error probabilities instead of 1 and display them all. So that is calculated by using this one particular formula. In this particular formula, what we estimate is what is the probability of encountering the combination that cannot be fixed. Yes. So starting with 1, that is the set of all possible outcomes. So correct combinations with 1 error, with 2 errors, with 3 errors, and so on and so on. from set all of the possible outcomes, what we want to now subtract is event when you receive code word without a single error. So error probability is some number. Yes, 1 minus error probability is the probability to receive a symbol correctly. If you have two symbols, C1 and C2, with an error probability, let's say, of 0.1 each, so the chances are to receive both correctly will be, so chance to receive first symbol is 0.9 correctly without error, and that doesn't affect the second. Yeah, so the second symbol also is of 0.9, and the probability of these two events happening at the same time is product, which can also be written like 0.9 of 2. So that is the probability to receive m symbols in row without a single error, which is fine because our code is not going to do anything bad to that, and this is not an error. Yes, so we exclude those. Now this is the probability of receiving g correctable errors. For Hamming code, g is equal to 1, so essentially this summation goes away, and this number of combinations essentially converts to m. So what we have here is now error probability at the power of 1 multiplied by 1 minus error probability at the power of m minus 1. So that means you receive one symbol with error followed by m minus 1 symbols without error. So this is one error per code word, and it can happen in m possible ways. So we subtract that also because this is a guaranteed correction from our Hamming code. So Hamming code can deal fine with this type of errors. And what is left over is anything that Hamming code will not be able to deal with. So we'll find that probability by calculating this formula. Again, for the, how we can say, economy of space, I'm going to create an anonymous function here, which is going to be called tech of x. Also, I need to specify what is my m, because that is going to actually affect a lot. You would agree that having 7 symbols in row without error is easier to achieve than having 31 symbols without a single error in a row. Yes, so that actually depends on your m parameter, which is specified here. For me, m parameter is 7. Yes, so I use that one. So that means m is equal to 7, the Hamming code word length. It doesn't matter if it's a cyclic code or group code at this point, both of them have the same efficiency. So now that will be argument x, and then the function itself, which is 1 minus x, no, wait, 1 minus 1 minus x, so x is probability, yes, at the power of m. Now this m is read from here, so it's known. So that is the probability of receiving no errors, minus m times probability of one error multiplied by 1 minus error probability at the power of m minus 1. So probability of receiving one symbol with error and rest without, and in m possible ways, because your error can be in the first position, in the second position, in the third position, in the mth position. Yes, m possible ways to receive one error, and all of them are going to be fixed. So we want to exclude all of them. So finally, I do some fprintf statements. So top 2 plus errors probability for BASK, %e new line, and here I have PR deck for PRBASK. BFSK and BPSK. So with that in mind, we can now actually estimate these probabilities of errors, which is now you can see for amplitude shift keying, that's going to happen once per 10,000 blocks, yes, which is considerable. Probably, yes, probably we shouldn't use Hamming code at least for 12 decibel signal to noise power ratio for amplitude shift keying in such conditions. So maybe it's better to use another code. For frequency shift keying, that's now once per 100 milliamps, yes, which probably is going to be fine. We can deal with that. That once in a you can say gigabyte, yes, or so, you will have to retransmit 1 byte, yes. That probably is fine. And here, obviously, it's completely fine that once per, I don't know what is this converted in bytes, yes, if the positive degree, of course, you get one more than 2 errors. That's just going to happen very rarely. So we assume that probably shouldn't use Hamming code for amplitude shift keying in this scenario. But again, this depends on signal to noise ratio, SNR, because if I were to specify SNR, signal to noise ratio 15 decibel, the situation will change significantly. Yes, now we see that even amplitude shift keying shows exceptional result, but that's for the length of the code of 7. Now let me try to actually go back to 12 decibel and say I will use the code word of the length 31, which means there will be higher chance to encounter more than one error in 31 symbols than in 7, right? So that means that now our numbers are not going to be so good. Yes, and indeed they are. Now we are speaking about thousands here and tens of megabytes when you will have to retransmit 1 byte. When again, those are like no ready receipts, like should you use that code or should not. That's to be considered in overall, because easier codes obviously tax your processor also in less amount. Yes, they consume less power and they are easier to use. So basically, that has to be made a decision considering all factors. So that concludes our calculations for the course project. So as you have seen, we have went through quite a lot of tasks today, considering that you have created your Hamming or Shannon or Huffman or Shannon-Fano code. Now you should have task 1, task 2, task 3, task 4, task 7, and task 8 done. And we are left with these 2 tasks. And we already started speaking about this code, yes? So as you can see, what you will need to do, and perhaps those who have group code, systematic and not systematic, you can already start working on that, because I have shown you how to make equations today, how you can decode and encode message with 1 error, 2 error, and so on. Schematics we'll discuss on Thursday, yes? But for cyclic codes, that's after the holiday, after the Easter holiday, we'll start speaking about cyclic codes. And then we are also going to implement some programs. Finally, this 6th task is going to be arguably the most difficult part of the code for the course project, but again, you are not like required to finish all tasks. Yes, so if you consider that this task is too difficult for you and maybe you should spend some more time on exam tasks, just do it. Maybe you will get there more points overall. Yes, but just know that this is really for those people who mark to get the highest grade. Yes, especially the task with Hamming error correction code here. But again, I will guide you through. We will have some code templates, so it's doable. Yes, nothing impossible. Okay, thank you for attention. Are there any questions?
Was it being recorded?
Yes, I did record this one.
Could you please post it on the page?
Yes, I will add it. Yes, okay, so